Yeah, so example one here, we've got a couple of differential equations that we have to check for exactness, and if they're exact, then we have to solve them. Now, in both part A and part B, it's pretty easy to see that the given differential equations are of this form. In A, just rewrite this y prime as dy dt and multiply both sides by dt, and you'll see that what you have is exactly like this, except all of the x's are t's, and that's it. Yeah, but it's pretty easy to see that A is of this form. And for B, rewrite this y prime as dy dx, and then multiply on both sides by dx, and then collect all of the terms on the left side so that the right side is equal to 0, and then you'll see that it's of this form. And notice also that B comes with an initial condition, so our solution, which is going to be written in this form implicitly, will be such that we will know what this constant C is, because we have an initial condition in part B. Yeah? Okay, cool. So with this, in both cases, without too much work, it's pretty easy to see what M and N are. In A, without doing anything more, we see that this is M and this is N. So then if I write in black, we see that in A, my, the partial with respect to y of m, will be take the derivative of this, the partial derivative with respect to y, and so what I just circled. And so if you do that, you'd have to write 3t and then 3t and then plus 2y, right? 3t plus 2y. Okay, cool. And then if we look at n, and it's going to be sorry if we look at n, and it's going to be nt, so the partial with respect to t of n, we just take the partial with respect to t of this here, right? And if we do it correctly, we see that we have to write 2t and then plus y, right? And clearly they are not equal. My is not equal to nt, so therefore A is not exact. So let's move on to B, and if B is exact, then we'll be able to solve B. Yeah? Okay. Yes, I was able to backtrack enough. You can only backtrack so much, and yeah, I wrote just enough that I could backtrack and delete everything. Okay, cool. I was pretty excited about that. Anyway, B, right? So B, let's do a little bit of algebra, what I said you should do to get it to be in this form, so that it's pretty clear for everybody. So we have 2xy squared plus 4. That's fine. That's pretty nice as it is. And then we'll subtract, so minus, and then 2 times, and then it's going to be 3 minus x squared y times y prime, or dy dx, I suppose. We can go all the way in showing that it's of that form, and then I'll have to say equals 0, right? Okay, cool. And now if I multiply this on both sides by dx, and at the same time distribute this minus 2, then I'd have to write 2xy squared plus 4 times dx. Remember, I said I was going to multiply both sides of this previous equation by dx, while also distributing that minus 2. And then we'll write plus, and it's going to be distributing the minus 2, as I said. It'll be negative 6, and then plus 2x squared y, and then times dy is equal to 0. Now it's pretty clear that this is m and this is n. Yeah? Okay, cool. Alright, so let's make room. Get rid of this and slide this up. Right, as I said, we've got our m and n identified. So m and n, and we just need to check if partial with respect to y of m is equal to the partial with respect to x of n. Okay, the partial with respect to y of m is going to have to be what in this case? Well, it's going to be 4xy, right? is that equal to the partial with respect to x of n? Well, the partial with respect to x of n here, the negative 6 goes to 0, will be 2 times 2, so that's 4xy. Nice. 4xy. So the answer to question mark is yes. So that means that b is exact. And so because b is exact, we now need to solve it. Yeah? Okay. All right. So here's how you solve exact differential equations once you know that they're exact. It's pretty cool, actually, this solution method. And so here it is. But we need to first make room. And I need to also like reference this, so we'll keep it right there. That's good. All right, so here's what we can do. Remember, if you watch example 0, and you should, it will add an incredible amount to your understanding, so I really encourage you to watch example 0. If you watch example 0, you'll see that our solution is some function phi of xy equaling a constant, where if we take the derivative of this here, this equation, phi of xy equaling c, on both sides, that's where we get this form, m dx plus n dy. And it turns out that m is equal to the partial with respect to x of phi, and n is equal to the partial with respect to y of phi. Yeah? So knowing this, since what we need to do to solve our differential equation, this, which is the same as this, right? To solve this differential equation, what we need to do is retrieve phi, right? Since that's the task, we have two options. We could either integrate m with respect to x, that is, integrate this with respect to x, right? So we can try to retrieve phi that way, because we're going backwards, because m is like phi after taking the partial with respect to x, right? We could do that, or we could alternatively integrate n with respect to y. And so that's like doing this, which is right? Okay, so we could do either, and I'm gonna prefer the former for no good reason. Like I said, you can do either, but I'm gonna go with this route. And so if we do that, then and I guess I'll keep this as a reminder up here. If we do that, then we see that if we do this integration here, we see that since m is given by this right here, right? This right here, since that's m, our integral will look like this. It'll look like 2x y squared, and then plus 4, and then it will be dx, right? Okay, cool. All right. And so we go ahead and integrate, and when we do, we're gonna get x squared, y squared, and then plus 4x, right? And then plus some function, let's call it h of y, and then plus some constant k. So I'm letting this constant k be like a number, but this is a function, some function h of y, because like if I claim this to be phi, remember, if you take the partial with respect to x of phi to get to m, then anything that's strictly a function of y would turn to 0. It would hide, right? And when you look at just this guy, right? The partial with respect to x of phi, right? When you're looking at that, anything in phi that was strictly a function of y would have turned to 0. So when we're retrieving phi, just like a constant, we need to also recognize that we might have some function of y. Yeah. Okay. Cool. So that's that. And otherwise, now that this here is phi, right? That's phi of x comma y, and we have phi plus k, of course, this constant k here, which, as I said, is some number. Yeah, so since we know that this is phi here, we should be able to say that phi uh, um, partial with respect to y is equal to n, right? Okay, but that'd mean that if we take the partial with respect to y of this, we would have to write that we have, sorry, I'm saying like way too many times, but the and then the plus the 4x turns to 0, and then we'll have plus h prime of y, and plus the constant will go to 0, right? Like after we take it, we just took a derivative. All right, although partial. Anyway, the constant goes to 0. We got it. And now, so this here is supposed to be n, but we know n. N is right here, right? We know n. So what we need is for this to equal negative 6 plus 2x squared y. Yeah? Okay. Cool. I know you're following. Alright. So maybe like hold on, sorry guys. I'm trying to figure out what we get rid of. You know that this is phi plus k, so just jot that in your head. We need this space. So there that is. And I'm also gonna keep this so that we can compare that our final answer is of this form, right? Because we need it to be of this form. But anyway, here we are. Okay, so we know that n, by taking the partial with respect to x of literally our phi here, is equal to this. But on the other hand, we know n from our differential equation is this. So comparing the two, because they need to be the same, we see that this here is the same as that. So then it must mean that h prime of y is equal to negative 6. But then that'd mean that h of y is equal to negative 6y. So that means we don't have to be vague about that there. We could replace it with negative 6y. Yeah? Okay, cool. And I'm going to even keep the plus k, and I'll show you where we're going to go next. Like I said, you could have like kind of taken the route of going with integrating n with respect to y, but we chose this route, and so that's that. You would have ended up at the same place in the end, even if you took the other direction. Okay, so am I erasing anything important? Well, kind of. No. Okay, so need that, and just keep in mind that h of y we've just determined is negative 6y, so that I could also delete this. And so here it is. So we have a bit more left to do to finish. Not too much more, but a bit more. And that's this. Now we have that this is phi, and we even know h of y. So we see that phi is x squared times y squared plus 4x, and then minus 6y, which is h of y, plus k, and then equal c, right? So this here is the explicit form of our solution. And in fact, we don't need plus k equals c. We could just have k swallowed by c. And so we could just have one constant, so we could write this equals c. Now we need to determine what this c is, because we have an initial condition. Y of negative 1 is equal to 1. So that means x is equal to negative 1, and that will in turn mean y is 1 when x is negative 1, right? That's what this here means, right? Okay, so x is negative 1, y is 1. This is 1 times 1, so that's 1. And x is negative 1 again, so this is negative 4, so plus a negative 4 is just minus 4. And y is 1, so we have minus 6, which would mean that this is c, and that would mean that c is negative 9, yeah? Okay, cool. So, sometimes, as I said in example 0, you can turn your implicit solution into an explicit solution. Sometimes you just have to leave your final answer in the implicit solution form. But anyway, the right hand side here now, we know the constant c has got to be negative 9. So this implicit form is actually a case where we can turn it into an explicit form. So we can, from here, actually get an explicit form for y of x, our solution, right? Instead of leaving it like this. So how do we do that? Well, we go first, let's write this here, which is 5xy equals c, as where we know c now, right? As this. Well, let me next go to the minus 6y actually. You'll see why I wanted to do that. And then it will be plus 4x, and then it will be plus 9 is equal to 0. I claim that this is a quadratic in y. A quadratic in y can be written in the form ay squared plus by plus c. And if we're solving it, you can say equals 0. So I claim that this is a quadratic in y, and it is. Look, like it's this is a, this is b, and this is c. Yeah? Okay, cool. So we know that we can solve it using the quadratic formula. And we don't need this anymore, but we do need this space. So, and yeah, we could probably do away with this too. Well, no, actually, let's keep that because that's our implicit solution, right? That's our solution in implicit form. Okay, so yeah. So using the quadratic formula, we see that y, which is a function of x, which is going to be a function of x, is y of x is equal to minus b, so that's positive 6, plus or minus, and then it's the square root of what? Sorry, I want to use a ruler. Well, it wasn't my ruler ready. Okay. And it's the square root of b squared minus 4ac, which in this case is going to be 36 minus 4. A is x squared times x squared, and then c is 4x plus 9, and forgive, but it's all under the square root, so I have time to extend it. And then all of this is divided by 2a, which is x squared, right? Sorry, y'all. So 2a is 2x squared. Okay, cool. Now, one is how do we get how do we determine if it's plus or minus right here? So that's kind of straightforward, which is using the initial condition again. So since we know y of negative 1 is equal to 1, if we work out the details, we need 1, which is y of negative 1, right? Y of negative 1. We need 1 to equal 6 plus or minus the square root of what? 36 minus 4, x is 1, times, and then it's 4 times, x is negative 1, so it's, this is going to turn into plus, and then 4, and then times negative 1, well, no, sorry, it's x squared, so that's why I kept the 1. So it's minus 4, my bad, guys. And then x is negative 1, so this is going to be negative 4 plus 9 is 5. So minus 4 times 5, so that's just minus 20 from 36, so that's 16. And in fact, I'll get rid of the square root and write 4, right? Because the square root of 16 is 4. But we need to divide all of this by, we need to divide it all by 2a, which is just going to be 2 times negative 1 squared, or just 2. And we see that if we keep the positive, we'll get 10 divided by 2, which is 5, not equal to 1. But if we keep the negative, we see that we get 2 divided by 2, which is 1. So we see that here in this part, when we get to the quadratic formula part, we see that we need to get rid of the plus here. The final caution is before you say you're done writing this explicit form of our solution, and of course the implicit form is right there, but yeah, before you say you're done with this, you also need restrictions on x, because we can't allow x to be 0 because we can't divide by 0, and we additionally cannot have a negative in here. So before you say you're done, you have to take care of those two things. But my battery's dying, and I've had enough of this. And hopefully, I taught you a lot. So I'm gonna leave it at this. Yeah, I've had some like tech kind of glitches. I don't know if you saw like my mouse dragging. If anyone knows how to fix that, because I've been having issues. Like I'd write, and then my like computer would take over and start writing on its own. So if anyone knows how to fix that, please let me know. But otherwise, I hope you enjoyed this video, and take care. Example 2 to come soon.